chapter, chapter 9, is on conic sections. A conic section is a section from a cone, and with those sections you can easily make circles, parabolas, ellipses, and hyperbolas. We'll talk about those in this chapter, and in a later video I'll explain really what a conic section is and what that means. But today we'll just talk about circles. Let's find the set of all points with a distance of 4 units from the point 6, negative 3. For the record, when you hear the term set of all points, we could just be calling this the locus. Not locust, there's no T, it's not a bug, it's just the locus, the set of all points. I want to be 4 distance from the point 6, negative 3. Well, on this grid that I've set up, I'm going to call this the point 6, negative 3. That's going to be the center. One thing I really recommend is you don't always put your axes in the middle of your graph. Instead, put the center in the middle of the graph. So if that's the point 6, negative 3, then my x and y axis are going to be here and here. The x-axis is just above, it's 3 units above, and the y-axis is 6 units to the left. And I'm quickly just going to jot down some points to get this thing labeled. So 2,
4, 6, 8, 10, negative 2, negative 4, negative 6, negative 8.
Okay, I'm going to find all the points that are 4 units away from this one. Just like last time, the 4 right angle points are pretty easy. There's going to be one here, up 4, and left 4, and down 4, and right 4. Those 4 points are very simple, but I want more than that so I can actually sketch a good circle. It's hard to draw a good circle with just 4 points. It ends up looking kind of like a square with round edges. So we're going to find a couple more points that can fit onto this circle. If I again think about the distance formula, I'll write it out one last time. Distance is x2 minus x1 squared and y2 minus y1 squared. I'm going to call this my point x1, y1. That's one of the points from which I'm finding a distance of 4 units. So I know the distance is 4. I'm going to just take my x1 and plug it in right here. So this becomes x2 minus 6 squared, and this becomes y2 plus 3 squared. And I don't like having this all inside the square root, so I'm going to square both sides, and I get 16. And instead of calling it x2, I'm just going to call it x. So I get x minus 6 squared plus y plus 3 squared. The reason this is going to stand for any, this stands for any possible point. Any possible point can be 4 units away. We just have to find where it is. Now I know I can't plug in an x value bigger than 10 or less than 2. It's going to be too far wide. So I'm going to plug in, let's do 4. If I plug in 4 for x, 4 minus 2 is an even number, and an even number squared is kind of nice. So I'm going to go with that. So I'm going to plug in a 4 for x. If x is 4, this becomes 16 equals 4 minus 2 squared plus y plus 3 squared, which is really 16 equals 4, because 4 minus 2 is 2, and 2 squared is 4, plus y plus 3 squared. If I subtract the 4 from both sides, 12 equals y plus 3 squared. If I square root both sides, I'll get plus or minus the square root of 12, which if I wanted to, I could call that 2 root 3, but I don't really care that much, equals y plus 3. Subtract the 3 from both sides, and we get negative 3 plus or minus the square root of 12 is our y value. So we plugged in a 4, and we got out negative 3 plus or minus root 12. I'm going to find what that is on the calculator. Negative 3 plus the square root of 12 is 0.46. And negative 3 minus the square root of 12, negative 6.46. We'll call it negative 6.5. So you plug in 4, you get out 2 things. We'll call it 0.5 and negative 6.5. I didn't write those very nicely, so I'm going to clean that up. That means there's a point here . There's a point here and a point here. But again, I can use symmetries. This was 2 units away, so if I go 2 units over here, there's going to be a point here and a point here. And if I wanted to, I could take the steps. Like this goes up 1, 2, 3.5, and right 1, 2. That was up 3.5, right 2. I can now go right 3.5, 1, 2, 3.5, up and down 2, and find more points like this. What I'm doing right now, you might find kind of confusing, and I understand that, and I can live with that. If this last part is throwing you off, don't worry about that. But the point is, if I were to plug in 2.5 for x, I would get out something kind of clean for y, like -1. And I also get something else out. I have a bunch of points now that goes like this. Using the symmetries of the circle to my advantage, I was able to find the set of all points with a distance of 4 units from the center point. So here's the equation that lets me find the set of all points, this equation right here. Here's a table that found a few of them, but here's the actual graph showing all the points that are 4 units from 6, -3. This is the general equation of a circle. X minus h squared plus y minus k squared equals r squared. The center is at the point hk, and the radius is r, not r squared. So like right now, if we're going to graph this equation, this has a center. Try and figure out where the center is and the radius before I tell you. The center is at -2, 3, and the radius is 4. It's not 16. Square root the 16 to get r. R is your radius, not r squared. So as I said, I'm going to put the center of the circle in the middle, which means that this is my y-axis, and this is my x-axis here. So there's -2, 3. I'm going to quickly throw down a few numbers, counting by 2s. And I will do the radius of 4. If the radius is 4, let's go with a nice hot pink here. I know I've got a point here, 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 and here. If I wanted to find any more specific points, I could make a table and plug something in for x or y, it doesn't matter. Plug something in for x and get something else out for y. But here's another trick I have to find 4 more locations of points. Not their exact coordinate, but at least how to plot 4 more points really simply. I'm going to think about the diagonals. And by diagonals, I mean if I was going 45 degrees in any direction, 45 degrees from the center, so like 45 degrees here, 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 and here. If I take the radius and do the radius times 0.7, in this case that's 4 times 0.7, which is 2.8. If I count out 2.8 diagonals, there's 1, 2, 0.8 would be like here. If I count out 2.8 diagonals in all directions, that gets me 4 more points on the circle. Now I've got 8 points without doing hardly any work. I don't actually know the coordinate of this point. Like it looks like it's -4.8, 5.8, but I don't know. In fact, I know it's not that exactly. But I can at least from these points sketch out a nice curve for my circle. If I wanted to find other actual points, I'd have to just plug in numbers for x and y. If you're wondering why it's 0.7, it's really a trig conversation. 0.7 is the same as √2/2. So you're multiplying by √2/2, and that probably doesn't help you at all, but it will someday. If I wanted to graph all the points that were further away than 4, if the radius was greater than 4, I'd be shading everything out here. Everything out here has a distance of more than 4 units from the circle. So that would be a greater than. A less than would be shaded inside, a greater than shades outside. Okay, we've got 2 more problems. A rectangle is inscribed in the circle x squared plus y squared equals 36. And the rectangle has a vertex at point 3, comma y. We don't know what that y value is, so it's 3, comma something. Find the area of the rectangle. Well, this right now, this equation has an h value of 0, a k value of 0, and an r value of 6. So my center is at 0, 0, and my radius is 6. There's points here, 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 and here. If I do the radius times 0.7, I get my diagonals. I'm going to count out 4.2 diagonals. 1, 2, 3, 4, 0.2.
1, 2, 3, 4. 0.2, they're probably a bit too far out. 1, 2, 3, 4. 0.2, and 1, 2, 3, 4. 0.2.
But I'm going to cheat and use a circle drawing tool. You can too, I don't mind. Do some by hand and some with a tool if you've got it. Yeah, that's pretty good. This is every point that is 6 units from the center. That's what that circle is showing. X squared plus y squared equals 36. Well, there's going to be a rectangle located someplace with the point 3, comma y. So someplace here. I don't know exactly what that coordinate is. I don't think it looks like it's at the point 3, 5, If I plug in 3 for x and 5 for y, I'm going to get out 34, not 36. So it's actually a little bit taller, a little higher than the 0.35. It's like 3.51 or 52 probably. But there's some rectangle that is inscribed in this circle. Now, we're going to assume, it might actually not need to be assumed, but we're just going to assume that this rectangle is going to look like this. If it's inscribed, that means that every corner of the rectangle is on the circle. So that's the only rectangle possible where that happens. We're going to find the area of this rectangle. To do that, we need to find this coordinate y. So I'm going to plug 3 in for x into a table, into the function. If I plug 3 in for x, we get that 9 plus y squared equals 36. I plugged 3 in for this x right here. So that means that y squared equals 27. So y equals plus or minus the square root of 27, which we can call 3 root 3 if we want to, but that's not super helpful. I'm still just going to calculate the square root of 27. 5.2, we'll say. You plug in 3, you get out plus or minus 5.2. Because this circle is centered at the center, 0, 0, I could actually do plus or minus 3, plus or minus 5.2. So this is negative 3, negative 5.2. This is, oh, that's positive 5.2. This is negative 3, negative 5.2 right here. This is 3, negative 5.2. And this top right corner was 3, 5.2. There's a couple ways to find the area of this rectangle. The simplest way is we figure this length right here. This length right here is 10.4. We know that because it's two 5.2s. In the same way, this length right here is 6 because it's plus or minus 3. So if we multiply those, 10.4, that's a 10, not a 16, 10.4 times 6, we're going to get 62.4. The area of the rectangle is 62.4 units squared. That's a nice, quick, simple way to do it. Another way to do this that I think is really cool is we could take the x and y values at this coordinate and multiply them. If I do 3 times 5.2, I'm going to get out 15.6. That 15.6 is actually the area of this rectangle right here. I don't know if you've ever thought about this. I didn't until a few years ago, really. But if you multiply a corner point, any point, what you're finding is the area of the rectangle from the origin to that point, because it gives you the height and the width. 3 times 5.2 is 15.6. That's the area of this rectangle right here. Well, there's 4 of those rectangles. There's one here. There's 2, 3, 4. So if we do 15.6 times 4, we're also going to get out 62.4 square units. The symmetry of the circle makes this calculation fairly simple. You find a point here, you bounce it over to here, and here, and here. Last one. The circle x plus 4 squared plus y minus 2 squared equals 25 has a tangent line through the point negative 1, negative 2. A tangent line is a line that crosses a circle at exactly one point, so not what I just drew. Tangent lines have some pretty cool properties that we'll talk about after we graph this. This circle, it has a center at negative 4, 2, and a radius of 5. So if this right here is going to be the point negative 4, 2, I have to draw on my x and y axes. Try and think about where those are going to be before I do it. That is the point negative 4, 2. And let's just put on a few coordinates. Let me grab my circle drawing tool and make this look all pretty again. Here is a circle with a radius of 5. It's going out a little bit wide, but we're going to live with it. Okay, well this circle has a point of tangency at negative 1, negative 2. Now, negative 1, negative 2 is right here. Actually on the circle. Like if I plug in negative 1 for x and I plug in negative 2 for y, I'm going to get out 3 squared plus 4 squared, which does actually equal 25 because 9 plus 16 is 25. So that point is on the circle. It is 5 units away from the center. Well, a line of tangency, like I said, only touches at one point, and it's actually perpendicular to the line that's drawn from the center to that point. So it's perpendicular to this radius right here. I want to find the equation of this line, the rule of this line, which is going to involve having a slope and having either a point or a y-intercept. Well, to find the slope, I first got to find this slope. To find that slope, I just kind of count. It's going down 1, 2, 3, 4, and right 1, 2, 3. The slope of r of this radius that I just drew is -4/3. So the slope of the tangent line, we're going to use m for slope, the slope of the tangent line is going to be +3/4. To find a perpendicular slope, remember these are perpendicular lines, to find a perpendicular slope, do the opposite reciprocal. The next thing that I need is just any point. We already have a point here. So I'm going to write this equation in point slope form. That would be y plus 2 equals 3/4 times x plus 1. That is the equation written in point slope form. If I wanted to go through and convert that into slope-intercept form, I would distribute the 3/4 and get y plus 2 equals 3/4 x plus 3/4. Subtract the 2 from both sides, and I need to get some common denominator action here. That becomes y equals 3/4 x, and that's 3/4 minus 8/4, so that's minus 5/4. 5/4 is 1.2, which looks about right based on the graph that I have. There's the equation in slope-intercept form. That's the equation of a line tangent to that circle through that point. Sweet, we've done it. Circles are the set of all points equidistant from a fixed point in the center. They have a center at hk with a radius of r. The equation of a circle is essentially the distance formula. And the distance formula is actually just the Pythagorean theorem. If you multiply the radius of a circle by 0.7, you'll get the number of diagonals to travel to get estimate. And if you get really good in practice, you can become a world circle drawing champion, to which I will link in the description. It's pretty wonderful. Thanks, y'all. Have a nice day. We did it. We got through another math video. Thanks for watching. Here I'm going to play with the perspective on these shapes while I talk to you. Please subscribe to the videos, like the videos. Okay, let's start this thing over. You did it. You got through the video. Thanks for watching. I'm going to play with the perspective of these shapes, which is always pointing towards that center while I talk to you about things. Please subscribe to the video, the channel really. Please like it if you found it helpful. If you want to share it with friends and say, hey, this guy's not the worst, that's an option too. You can always take your video quiz if you're in my class. And comment down below. See you next time.